Okay, I've got a study sheet for the final exam, similar to the study sheet for the midterm. Let me just emphasize, the final exam is cumulative. It covers what we've done since the midterm, but also the material that was on the midterm. The study sheet is not cumulative. Okay, the study sheet is just the stuff since the midterm. So thanks, Adam. The study sheet for the midterm lets you know what the key terms are for that material. Actually, can I grab one of those before you pass them on? Thank you. Okay, this is just hot off the presses. I was really pestering the room assignment guy to give me the rooms for the final exam so that I could put them on the study sheet, and he couldn't do it, and then as soon as I Xeroxed all those copies, he gave me the rooms. So it's not in your study sheet, it is on the board. Okay, the final exam is 1 week from today. It's from 3 to 6 p.m., okay, late afternoon. Adam's and Emily's sections will take the exam in this room. June and Flory's sections will take it in Perloff 1102, this room right here. Off the top of my head, I'm not thinking where Perloff is, but you guys have a week to figure that out. Is it one of those buildings that's by the law school? It's real close. Just right across the street here? Oh, okay, good, very good. So I'll be splitting my time between the two rooms. You will not need a blue book for the final exam. Okay, in contrast to the midterm, I'm going to give you space on the sheets to write. Okay, so don't need to bring a blue book. Same story with calculators as it was on the midterm. You can use one if you want. You don't really need one. Okay, there's no need to turn fractions into decimal points or anything like that. All right. Today we're going to finish up our discussion of Grimm trigger. Everything that you're responsible for on the final exam will be covered today. The main thing we're going to do on Thursday will be review for the final. So one thing you might want to do before Thursday is take a look at that study sheet, take a look at some of the problems, go back over your notes. Thursday will be basically, the agenda will be up to you guys. Okay? You can ask questions. I'll do my best to answer them. If you know already that there's something you'd like more help on, something you'd like me to go over again, if you email me beforehand, I can probably prepare a more elaborate, more organized answer than I'm necessarily able to do off the top of my head. Sometimes I do okay with that, sometimes not so. Okay, so if you can give me a heads up about things that you'd like to cover on Thursday, that'd be good for everybody. All right. So the first thing I want to do today is I want to talk about repeated prisoners' dilemmas where the payoffs aren't symmetric, okay, where the two players aren't completely identical in terms of their payoffs. You've got a problem like this on your homework. That's the reason why I extended the homework deadline to Thursday, was because I hadn't yet done the example. So I'm going to just make a small change to the prisoner's dilemma we were working with last week so that the players aren't completely the same and their payoffs are not completely symmetric. Okay. So we're going to leave player A the same as player A was last week. Same choices: slack off, work hard, B, slack, work. And A's payoffs are intended to be exactly what they were in last week's game. Okay. Reward payoff of 3 if A works hard and B works hard. A punishment payoff of 0 if both A and B slack off. A temptation payoff of 5 that A gets when A slacks off and B works hard. And a sucker payoff of -2, which is what A gets when she works hard and B slacks off. Okay. So what I'm going to do here is I'm going to leave B's payoffs from working hard the same as they were last week, but I'm going to make B a little bit lazier than A. Okay. I'm going to say that B's payoffs from slacking off are a little bit higher than they were. Okay, so B's getting 1 instead of 0 here, and 6 instead of 5 for the temptation payoff. Okay, so just being clear, what I mean about asymmetric payoffs here is that now when B is in an identical situation to A, like in this case where B is working, let me point to B's payoff, where B is slacking off and A is working hard, okay, in this case, B's payoff is different from the payoff that A gets when A is slacking off and B is working hard. Similarly, B's payoff from slacking off when A slacks off is a little bit higher here. So they're not completely the same. And what this means is we're going to have to look at Grimm trigger separately for each player. Last week, when the two players had exactly the same payoffs, we found that as long as both of them had a discount factor of at least 0.4, then Grimm trigger would be in equilibrium. Okay? By that, just repeating, we mean that if the other one is playing Grimm trigger, neither one has any regrets from playing Grimm trigger. They won't do better by deviating to an alternate strategy. We only needed to do the analysis once for those two players in the case where their payoffs were the same, but now the payoffs are different, so we're going to have to analyze Grimm trigger first from the point of view of player A and second from the point of view of player B. What it means is that the minimum discount factor for A is going to be different than the minimum discount factor for B. Okay? That's the bottom line here. When the payoffs are asymmetric, then each player has a different condition for Grimm trigger to be a Nash equilibrium. Okay? And what I mean by condition is a different minimum discount factor. Okay. Okay. Well, this isn't too bad because I didn't change A's payoffs from last week's game. Okay. So we know what A's condition is. We know that if, let's write the question up here. If we're looking at when is Grimm trigger a Nash equilibrium, for player A, what we need is a discount factor that is at least 2/5. And now, because each player has a different discount factor, I'm going to put this little a here. Okay, this tells us how impatient A can possibly be. As long as $1 tomorrow is worth 40 cents or more to A today, then yes, Grimm trigger will be in equilibrium for player A. Okay, but we have to look at player B separately. Okay. Another issue that I want to go over in the context of this example is what part of the Nash equilibrium argument you guys have to derive each time. Okay? Last week, you'll remember, I looked to see whether A could gain by deviating to 3 different types of strategies. Okay? I compared the payoffs from Grimm trigger to the payoffs from defecting unconditionally. Okay, that's one thing that A could do differently than Grimm trigger. I compared it to the payoffs from cooperating for a while and then defecting. That's another thing that A could do that's different from Grimm trigger. And I compared it to the payoffs from defecting and then cooperating later. And what I showed you last week is that the most tempting deviation, the alternative strategy that is going to pull A away from Grimm trigger, is unconditional defection. Okay, I showed that if A doesn't think that unconditional defection is a better choice than Grimm trigger, none of those other possible defections are going to be a better choice either. You guys can make use of that. Okay? On your homeworks and on the exam, you don't need to go through deviation number 2 and deviation number 3. I gave you that information and it is yours to use. What you do need to do for each problem is to see when Grimm trigger is at least as good as what you get from unconditional defection, because the answer to that, the condition that makes that true, is going to vary from game to game. Okay? So just again to repeat, the part of last week's argument that applies for Grimm trigger in any repeated prisoner's dilemma is the fact that the most tempting deviation is unconditional defection. Okay? That's always the thing that you're going to worry about. Okay? And you don't need to prove that. You can use that fact. What you need to do then is apply that fact and say, okay, when for this specific game does unconditional defection look like a better alternative? Okay, so that's what we're going to do right now. What I'm going to do now on the board is the part of the analysis that you guys do have to go through for every repeated prisoner's dilemma that you analyze. Okay, so what we need to do is look at when is the present value to be of Grimm trigger at least as good as the present value to be of, I'm just going to write defect here. But what I mean here is defect always. Okay? Always play the dominant strategy in the stage game. All right. So this is the inequality that's going to give different conditions depending on the payoff. So let's get an expression for each side of the inequality. So I'm B. The present value to me of playing Grim Trigger, if my partner is playing it, what am I going to get in the first round? I'm B. I'm playing Grim Trigger. What am I going to do in the first round? I'm going to cooperate. A's playing Grim Trigger 2, right? That's the Nash equilibrium condition. What's my payoff going to be? 3. Okay, what about next time? 3 again, right? I played Grim Trigger, and A played Grim Trigger, and we both cooperated, and Grim Trigger says, keep on cooperating as long as there has been no defection. Okay, so I'll get 3 in the next period. That's discounted. 3 2 periods from now, and on and on and on. As we did last week, I can reduce this infinite geometric sum. I can use the formula and write that as 3 over 1 minus delta. Okay, I'm applying that formula for the sum of an infinite geometric series. The formula works when the discount factor is strictly between 0 and 1, and discount factors are strictly between 0 and 1. So that's all good. All right. What's the present value on player B of defecting? 6. What do I get in the next period? It's not 0. Okay, I changed both of these payoffs. Okay. What do I get in the second period? 1 again, right? I'm going to get these forever. Okay, so I'm going to have to do a little more work here to put together the, to put this in the form of the geometric sum. Okay. So what I'm going to do here, I'm actually going to write out a few more terms. Plus delta cubed plus delta to the 4th. Okay. Remember what I said last week. Sometimes you'll see geometric sums that don't completely fit the formula. Okay, this side of the equation doesn't completely fit the formula for the geometric sum. Okay, and there's 2 issues. One issue is that there's this 6 here. Okay, that's not a problem, right? We can just carry the 6 around by itself and just focus on this. But there's still an issue here, okay? There's still an issue here in that what we're adding up doesn't start with 1. It doesn't start with delta to the 0 power. It starts with delta, okay? So what we need to do is we need to do a little bit of algebra here on this infinite sum. Let me remind us that it is, in fact, an infinite sum here, to get it so that it matches exactly our formula, okay? And to remind you of what the formula looks like, the formula is for the sum as I goes from 0 to infinity of delta to the I power. And if we write that out, let's write it out so we can gaze at it. The first term in this sum is delta to the 0 power. Well, anything to the 0 power is the number 1, and then we get delta plus delta squared plus delta cubed. So there's actually several ways to manipulate this to get an expression that exactly fits the sum. The one that is most appealing to me is I'm just going to factor out a delta here. Okay, so this is 6 plus delta times 1. I'm factoring out a delta here, so here's one of my deltas, here's the other one. I'm factoring out a delta here, so here's one of my deltas, here's the other 2. Another thing we could have done is we could have just broken up the 6 into 5 plus 1 and done it that way too. You get the same thing either way. Okay. So now what I have here in my parentheses is something that fits the formula. Okay, and that's what I'm looking for here. All right, so the present value to B of unconditional defection is 6 plus delta over 1 minus delta. Okay? So slightly more work. Very slightly more work. And yeah, I think I'll stick with this board. So everybody see what I did here? Everybody convinced I did it right? Okay. All right. So back to this question. When is this greater than that? Okay. So Grimm trigger is a Nash equilibrium when the present value of Grimm trigger, that's 3 over 1 minus delta, is greater than or equal to the present value of defecting, 6 plus delta over 1 minus delta. Okay, that's my condition. Okay. This by itself, in one sense, is an answer to the question. When is Grimm trigger in equilibrium? Exactly when that's true. It's not the most helpful form of the answer, though. The nicest way to think about when we can have cooperation in the repeated prisoner's dilemma is to think about how patient the players have to be. That's a natural way to interpret the situation. Okay? How much weight do they have to put on the future? In order to do that, we're going to take this condition and solve it for delta. That's going to give us our minimum discount factor, just as we did before, as we did last week, to get the 2/5. Okay? So working towards that, I'm going to multiply both sides by 1 minus delta to get rid of the fraction. Okay, so multiplying this side by 1 minus delta, 3 greater than or equal to 6 minus 6 delta. I'm just multiplying the 6 through by the 1 minus delta here, plus delta. Okay, so this is going to give me negative 5 delta. I'll bring that over here and bring the 3 over here. 5 delta needs to be greater than or equal to 3. Delta needs to be greater than or equal to 3/5. Okay. Anything you want to add to that? It's something I want to add to this. Okay. We put this A here to remind ourselves that this is A's minimum discount factor. And let me write that. This is A's minimum delta. That's what this denotes. Okay? This is B's condition. So let's put a B there. In fact, it wouldn't be bad to have used a B here all along. This whole analysis just applies to person B. Okay? Last week, we were looking for a single discount factor because we were assuming in the game that the two players were basically identical. They had the same payoffs in the repeated prisoner's dilemma, so they were going to have the same condition. Here, they have different payoffs, so there's a different condition that applies to B's discount factor. Than there would be to A's. Okay. So here we have B's minimum discount factor. Okay. So if both of these guys had, I'm going to get your question in just a second, Monica. If both these guys had a discount factor of 0.5, Grimm trigger wouldn't be in equilibrium. Okay, A would be willing to play, A having a discount factor of 4 or 5, A would be willing to play Grim Trigger if B was doing it, but B wouldn't. Okay, B would be too impatient. Okay, B's discount factor of 0.5 would be less than 3/5, and what that would be saying is that B would rather just defect. Okay, and this, if you think about it, this makes sense. What did we do? We made B lazier. Okay, we made B's payoffs from slacking off higher. Okay, so what that does is it makes B's temptation in the short run to defect higher, and we didn't increase B's payoff from cooperation. Okay, so those future rewards are smaller for B compared to what B's getting from defecting right now in the present. Okay, and that's the reason why B has to put even more value on the future than A does. Okay, now Monica, you had a question. This part right here? Yeah, well, I was doing kind of a lot of steps here. So what I was doing is 1 minus delta here, 1 minus delta here, 1 minus delta here, canceling, and then also distributing the parentheses. Okay, that's... Okay. Okay, so the take-home point here, when you have players with different payoffs, it's still a prisoner's dilemma. Okay, even though the payoffs are not perfectly symmetric, it's still the case that both players have a dominant strategy to defect. Okay, it's a dominant strategy for A because 0 is greater than -2 and 5 is greater than 3. It's a dominant strategy for B because 1 is greater than -2 and 6 is greater than 3. Okay, so they both got that dominant strategy, and when they both play the dominant strategy, the outcome we arrive at is Pareto inferior to what they would have done if they'd played the dominated strategy. That's what makes it a prisoner's dilemma. Don't need to have exactly the same payoffs. When you have asymmetric payoffs, you have to have a condition for each player, okay, and they will be different. Okay. How many of you guys did this part of the problem without me showing you? Just out of curiosity. A few tentative, small hands, not many people. Most of you just didn't try? That's fair. That's fair. I know you're busy this time of the quarter. Okay. All right, so the last thing I want to do with, yeah? Yeah, so Elaine's kind of looking for more of the logic here. And it's a big picture question in some sense. Why is it that making the payoffs different makes the minimum discount factors different? Okay. These, well, the ones here, these are the numbers that are different for player B than they were for player A. Okay, so one way, I think I'm going to try and answer that question a couple of different ways. One way to see it is to just kind of look at the math of it. When we're looking for the answer to this question, we're always looking at this kind of inequality. When is the discounted present value of the strategy in question at least as good as the alternative strategies? Okay, so we're always writing down this inequality and then looking to the game to figure out, okay, well, what is the present value of Grim Trigger? What is the present value of defect? At this step, when we start putting numbers and variables on the present value, that's when we start bringing in numbers from the payoffs. Okay, so one way to just kind of see the math of it is, since the details of this inequality come from the payoffs, that's one reason why we have to do it differently. Okay, so just the pure cranking away the algebra, you see that if you change a number here that's going to go into my condition, that it's going to change the value of delta. The other way to think about that is to think about it from kind of the logic and intuition point of view. Okay? If you're changing the stakes of the game, and I'm really focusing here on changing the temptation payoff, although all of them matter. What you're doing is you're increasing B's temptation to defect. Okay? You're increasing what B gets if B double crosses A the first time around. Okay? If B slacks off and A works hard. Okay? So all of a sudden, B has more to gain from slacking off now, even given that she'll be punished for it in the future, than A does. What that means is, in order for B not to slack off now, in order for that temptation to slack off to be offset, the future has to loom even larger. Okay, so that's, again, that's the logic. B has to care more about the future to be willing to overcome this greater payoff. Okay. And actually, with that question in mind, what I want to do is I want to go to a more general Grimm trigger example, one that has more variables in it, to make a few other general points about Grimm trigger and about cooperation in the repeated prisoner's dilemma. And kind of my idea here is to take our focus less on specific numbers in a game and more on the general logic. Okay, so that's what I'm going to do. I'm going to erase going towards the game, so if you think of questions along the way, speak up. Okay. So something I've been saying kind of all throughout the course is that those numbers in the payoffs are nice for learning game theory. They're kind of nice and concrete, and we can get answers that we could talk about. But they are just a complete fiction. Okay, we don't really know. We can't really assign numbers to people's utility in most situations. But what we often can do is we can rank outcomes. And whenever I've brought this up, I've said that when social scientists use game theory in general, we usually don't put numbers on the payoffs. We don't put numbers on all of the payoffs. We use variables and make assumptions about the variables. The prisoner's dilemma is used so often that there's even kind of a conventional set of variables that you'll see used over and over again. And if you find yourself, writing a paper for a class or wanting to use this kind of logic, this is a nice set of variables to use. It's the general form of the prisoner's dilemma. Okay, so I'm going to also use the general language. The choices are to defect and cooperate. Okay, we're going to have two variables here that are going to correspond to the temptation and the sucker payoff, but we are going to use numbers for defect, and cooperate, but these are nice numbers. Okay, what's the difference between 1 and 0? Well, that's kind of arbitrary. We don't know what these payoffs, what kind of units they're really measured in, but we're saying here, well, let's just define the difference between 1 and 0 as being the difference between what we both get if we both follow our own short-term incentive versus what we could have if we both cooperated. Okay? So 1 and 0 are nice, simple numbers to work with. Let's put them in the logical places in the game. And then the rest of the details that would distinguish one particular scenario from another, let's leave those as variables. Okay? And in particular, let's have A be a number that is strictly greater than 1. Okay, and this is going to be the temptation payoff. Okay, so here's B's temptation payoff when I defect and A cooperates. Here's A's temptation payoff when I defect and B cooperates. And let's put in minus B here as the sucker payoff. Okay, so B we'll say is a number that's strictly greater than 0, and therefore negative B is the sucker payoff. Okay, so these are variables. If this was a game where asymmetries were important, I could always index these with B. If this is player A and this is player B, I could say this is A's temptation payoff, this is B's temptation payoff, this is B's sucker payoff, this is A's sucker payoff here. Okay. I'm not going to do that for the rest of the analysis. I'm just saying that's what you would do. Okay. All right. So we're going to stick with the idea of symmetric payoffs here, which again, I guess it's good, in a way, this last week to be touching base with a lot of the issues that we raised in the first week. You might be wondering, well, why am I just showed you how you could set up a game and allow the two players to have different temptation payoffs, different sucker payoffs. And then I just said, well, I'm not going to do that right now. Why am I making that decision? Why do people make that kind of decision? It depends completely on the context. If I want to emphasize a point about one player being different from the other, if that's the context in which I'm using game theory, in which I'm making a game theoretic argument, then yeah, I'm going to make sure that my variables are different. If that's not the main point, I'm going to make everything else as simple as possible. Okay? When you use game theory, when you do any kind of mathematical modeling, that's the kind of rhetorical strategy you want to use. You want to think about what is your main point. Let that be the focus of the game and keep everything else as simple as possible. Okay? So right here, we're not focusing on differences between the players. We're just going to focus on the general structure. That's the reason why I'm assuming that the payoffs are the same. These two conditions are important, right? If either of these conditions fail, the game's not a prisoner's dilemma. Okay? If A is not strictly greater, it has to be a strict inequality. It can't be greater than or equal to. If A is not strictly greater than 1, then we're not going to have a dominant strategy to defect. And similarly, if B is not strictly greater than 0, we're not going to have a dominant strategy. Okay? So both of these are the conditions that make the game a prisoner's dilemma. Okay? It's only a prisoner's dilemma if, in this scenario, in this setup, A is strictly greater than 1, B is strictly greater than 0. Okay. Okay. So because we're back in the world of symmetric payoffs, the minimum discount factor for Grimm trigger to be in equilibrium in this game is going to be the same for both players, so I can just do it once. Okay? So I can ask my question, when is Grimm trigger a Nash equilibrium? Okay. As always, the answer is when the present value of Grimm trigger is greater than or equal to the present value of unconditionally defecting, just exactly the same as before. So, going right along, I'm playing Grim Trigger. What am I going to get? What am I going to get in the first round? One. I'm going to get 1 in the first round. I'm going to get 1 in the second round, 1 in the third, all the way out here to infinity. So I've got here, it's very nice with this payoff of 1 here. It's just the infinite stream sums to 1 over 1 minus delta. Okay. What do I get if I defect? What do I get right now, this first round? 0. No, no. He said it. A. Okay? If we both defect, we get 0. Okay, let's go back and emphasize. Both of these conditions assume the partner plays Grim Trigger. Okay? So what this means in the first round is, regardless of what the player whose actions we're looking at, whose strategies we're looking at does, the partner will cooperate. Okay? Because the partner is playing Grim Trigger. Okay? Just can't emphasize enough that this is the Nash equilibrium analysis. We're comparing one player's payoffs, holding the other player's strategy constant. Okay? So regardless of what this player does, the other player is going to cooperate in the first round. But now in the second round, what's the opponent going to do? Now the opponent is going to defect. Okay, the opponent is still playing Grim Trigger. The opponent is playing the equilibrium strategy, but the equilibrium strategy says, if you defected against me last time, or if anybody's defected, I'm going to defect. And now, in the future, all of our payoffs are going to be 0. I'm just being totally redundant, writing this in here to emphasize that all future payoffs will be 0 in this formulation. Okay, so again, you see how nice and simple this version of the repeated prisoner's dilemma is. Okay? So, putting these two things together, Grim Trigger is a Nash equilibrium when 1 over 1 minus delta is at least as big as A. Okay? What I get now and over the whole indefinite future string of interactions, what I get is at least as good at what I get from defecting now and then taking my punishment in the future. Okay, so there's my condition, right? And actually, it's kind of interesting to look at it this way. Okay? Here we have A by itself. So one way we can interpret this condition is this gives us the maximum value of A. Okay? So you tell me how impatient you are, and I'll tell you how big a temptation you can face in the short run in order for Grim Trigger to be in equilibrium. Once the temptation, remember that's what A is. A is the temptation payoff here. What I get when I defect and you cooperate. Once A gets above this maximum value, it doesn't matter that I care about the shadow of the future. I don't care enough. The temptation is just too strong. As long as the temptation is below this value, I'm okay. Okay? So this is one way to think about the Grim Trigger condition. The same condition, if we do what we did before, can still give us a minimum discount factor as well. Okay, so if I just multiply both sides by 1 minus delta, I get that 1 has to be greater than or equal to, just as I did before, I'm multiplying 1 minus delta times a, so I'm getting a minus delta a. So delta a greater than or equal to a minus 1, and delta has to be greater than or equal to a minus 1 over a. All right? So it's the same condition. These are just alternative ways of writing the same thing. These are both alternative ways of writing this basic Nash equilibrium inequality. This way gives us our maximum value of delta. Okay. So two ways to understand the conditions that support Grimm trigger as a way of getting cooperation in a repeated prisoner's dilemma. One way is to say, you tell me how impatient the people are, and I'll tell you how big their temptation can possibly be before Grimm trigger will no longer work. Okay, I'll tell you the maximum temptation. The maximum temptation is going to change depending on how impatient the people are. Or you could switch the roles. You could say, you tell me how big the temptation is in the short run, and I'll tell you how patient they have to be. Okay? Just different ways of looking at the same scenario. But they're both, there's this kind of balance aspect here. The weight that you put on the future, how much you value those future high payoffs from cooperation, has to be balanced by, it has to at least balance the temptation to defect in the short run. If the temptation is too high, Grimm trigger doesn't work. If the shadow of the future is too small, Grimm trigger doesn't work. Okay. I also want to say something about this. Okay? This gives us actually some very good news if we look at this. For any value of a that's greater than 1. Okay, remember, we're only interested in values of a that are strictly greater than 1 because otherwise the game isn't a prisoner's dilemma and this whole story doesn't make sense. As long as a is greater than 1, okay, this is always a number that is between 1 and 0. Okay? No matter how big a gets, a could be, say, a equals 3,000, then delta has to be greater than or equal to 2,999 over 3,000. Okay, that's a number that is extremely close to 1, but it's still not 1. For any temptation that you face, there is some degree of patience that will allow people to cooperate in the prisoner's dilemma. You can never have a temptation so high that nobody will ever cooperate. It might be an unrealistic level of patience. Okay, that's a darn high discount factor. It's unrealistic, but it's not truly impossible. Okay? What this is saying is that you can never completely rule out Grimm trigger as a possible way of cooperation. That is like really, really good news. No matter how high the temptation payoff is, no matter how perverse the incentives are in a particular repeated prisoner's dilemma, if people are just patient enough, they can cooperate. If people are just patient enough, Grimm trigger can be in equilibrium, and we can get to this happy outcome where we're cooperating, where we're both doing better over and over and over again, instead of both of us ending up with this cruddy payoff because we follow our short-term incentives. Okay? Right. So that is a point that, in one sense, I think is not obvious. I think when I just wrote this equation here, maybe some of you thought, oh boy, that means that we can always have Grimm trigger, but I bet a lot of you just didn't go there. It was certainly not obvious to me until somebody showed this. But on the other hand, it also just kind of fits with a lot of common sense things that we know about patients. Okay? One thing I will bet is that all of you guys are all here at UCLA, you've done well in your lives, your parents did a good job of raising you. I'm guessing in most cases that they deserve some credit. And I bet one of the things that many of you got from your parents from a very early age is encouragement, admonishment. Your parents tried to get you to be patient. Okay? Don't give in to impulses. Think about the future. Think about the long-term consequences. Be willing to eat your string beans first so you can have dessert later. That kind of logic is an aspect of child rearing all over the world. And I think this is the reason. The better human beings are at deferring gratification, okay, at doing something a little bit unpleasant in the short run, not giving into a short-run temptation because of future rewards, the better they do. Societies are better when people are more patient, when people can forego the temptation to follow their dominant strategies in the short run because of future benefits. Okay? So that aspect of folk wisdom, that a penny saved is a penny earned, wait for dessert last. That kind of logic is reflecting this idea that patience is not only good for the individual, it is good for the individual, but it's also good for society. Okay? All right. I think I have one more thing, one more really important thing to say, and then a few more, I don't know, interpretive observations to make. Okay? So right here, you can tell I got the wind in my sails. I'm giving you really good news. This is so wonderful. If people are just patient enough, the shadow of the future looms large enough, we can solve those prisoners' dilemmas. We can have an equilibrium where there's cooperation. Okay, that is all really good. Now I have to go back and give you the bad news. It's not the only equilibrium. Okay? Grimm trigger can be an equilibrium, and it's a great equilibrium. When we're playing Grimm trigger, even though Grimm trigger has that very grim punishment phase, we're not going to see it. All we're going to see is good behavior. People overcoming their short-term incentive to cheat because of the shadow of the future. Okay, so that's good. The problem is there are lots more equilibria. Okay? And here's the worst one. We've been thinking about unconditional defection as an alternate to Grimm trigger, right? As something that players could do differently than Grimm trigger. We can also think about it as an equilibrium strategy as well. Okay, so let's think about that. Here's another Nash equilibrium. Both players defect always. That's a strategy, right? It's a strategy in the repeated game. It tells me what to do no matter what. It's very simple. And if my partner is playing it, do I have regrets from playing it? No. If my partner is such a bad guy, if no matter what I do, he's going to defect, I'm not going to have regrets from being a bad guy to him. Okay? If my partner is always following through on the short-term incentive, if my partner is going to defect no matter what, then if I'm always, as the role player, I'm always in this column, then my choice is between 0 and the sucker payoff. I'll take the 0. Okay? So yes, there's always some discount factor for which Grimm trigger is in equilibrium, for which we can get cooperation in the repeated prisoner's dilemma. But over here, no matter what the discount factor is, this is always in equilibrium. Even if we're both super duper patient, put a lot of weight on the shadow of the future. If what I think you're going to do is defect all the time, even if I value the future a lot, I'm going to defect all the time, and vice versa. Okay? So the stage game dominant strategy is always also a Nash equilibrium. That's the bad news. Okay. So in any situation that fits a prisoner's dilemma, it's always possible to have cooperation in equilibrium if the players are patient enough. It is always also possible to have nothing but defection, nothing but bad news, regardless of how patient the players are. Okay? So some very good news on the one hand, some very sobering news on the other hand. Okay? Now, when we first talked about multiple equilibria in single-shot games, we talked about it in the context of the prisoner's dilemma versus the assurance game. Okay? The assurance game was the game that looked like the prisoner's dilemma, except the temptation payoff was less than 1. Okay? In the assurance game, remember, if your partner is cooperating, you want to cooperate too. We talked about this with the room cleaning example, and I talked about the roommate that had a conscience and felt bad if her roommate cleaned without her. Okay? And then we had this discussion about the fact that there was a good equilibrium when they got the reward payoff and a bad equilibrium when they got the punishment payoffs. And one question that came up was, doesn't the fact that the one equilibrium is better for both players, doesn't that by itself make that equilibrium focal? And I gave kind of a wishy-washy answer to it. It was wishy-washy, but I think it was true. Sometimes yes, sometimes no. Sometimes the pure fact that Grimm trigger or any other kind of pattern of cooperation is better for both players can make that outcome more likely. Both players could say, yes, we're both better off, won't we go there? Not always. In particular, if there's been a history of bad behavior and both players expect the other one to defect, it's going to be a self-reinforcing pattern. Okay? So, a little bit of yin-yang here at the end of Poli-Sci 30. Good news and bad news about prisoners' dilemmas. Okay. All right, what I think I'm going to do is we're going to do course evaluations now. And I'm deliberately doing that because on Thursday I will open the class with a few other remarks on prisoners' dilemmas. We're now finished with everything you need to do the exam, do the homework. Okay, so we're finished with what you're responsible for the course. I'm saving a little bit of discussion stuff to if we need an icebreaker next week. But I am going to ask you to do the course evaluations. I hope that you will take some time, if you have any specific comments, to write them on the back. I always read them and do the best I can to implement them for future classes. I'm not supposed to stand here and glare at you guys while you do them, so I'm going to ask Flory to pass them out. And can you also put this on the board? Anyway, great, thank you. So then I'll see you on Thursday.